Hey guys, today we're going to be calculating the force on a moving charge in a magnetic field. This gets a little bit weird, so just get your brain ready to think a little bit outside the box. So, magnetic fields exert forces on charged particles that are moving. Well, they also exert forces on magnets, but they exert forces on charged moving particles, which we know as currents. Something that is a consequence of this is that a moving magnetic field or a field from a moving source will exert a force on a stationary charged particle because motion is relative. So if there's relative motion between the two things, a force is exerted, whether the field is what's moving or the particle is what's moving. There are two types of motion for charged particles. There is translational, where the whole particle moves through space, given by a velocity v. And then there's also angular motion. So particles have a property called spin, and a charged particle with spin will have a magnetic moment, is what it's called. And this magnetic moment allows the particle to interact with the magnetic field, causing some force. So there's both of those types of motion. Today we're going to be dealing only with translational motion, but it's that angular motion and the magnetic moment that gives substances or materials their magnetic nature. So the equation for the force, the magnetic force on a charged particle is given by this equation. The force equals Q, charge of the particle, times V. That is a V. I know it looks a little bit like a U with the typesetting. Q, V, cross B. So this looks like a regular multiplication symbol, but when you multiply vectors, there's actually two options for how to multiply vectors. There's a thing called a cross product, and there's a thing called a dot product. And the dot product will yield a scalar, and the cross product will yield a vector. So sometimes they're called scalar multiplication or vector multiplication, and cross product is the vector multiplication. And since we're dealing with force, which is a vector, we use the cross product between velocity and field to yield a vector. And that's going to become important here in a minute. A weird thing about cross products is that for direction, because this vector over here is going to have a direction, the direction is given by a right-hand rule, and it's important when you're dealing with the quantities that you deal with them in the correct order in the right-hand rule, which will become apparent here in a minute. So it's important that V cross B is in that order. If we had force equals Q, B cross V, we would get a different directional result. So the order is important here. It is not commutative. If you know your properties in math, it's not commutative. It's V cross B. And since we aren't really equipped to deal with cross products here, we are going to use a simplification for cross products. A simplification for cross products is that A cross B, like if you have two vectors, equals magnitude of A times magnitude of B sine of the angle between them. So if we're doing V cross B, that's equal to V, the magnitude of V times the magnitude of B. These little brackets mean magnitude sine of the angle between them. I'm not going to get into all of the detail on that because that's for a later thing, but that is where it comes from. So to find the magnitude of the force of a magnetic field on a charged particle, you multiply the charge of the particle times the velocity of the particle times the field at that point times sine of alpha, which is the angle between your field vector and your velocity vector. And if they're at right angles, you're doing sine of 90. Sine of 90 is 1. So you would just get QVB. And most of the time we're going to be dealing with field and velocity at right angles. To determine the direction of the force, The idea is that the force is perpendicular to the plane given by the field and the velocity. So if you got those two vectors and you make them into a plane, which is a flat surface, the force vector is perpendicular to that plane, which you can see in this picture down here. You've got two vectors, field and velocity, lying flat on a plane with an angle alpha between them, and the force is perpendicular to that plane. Now, you may know or may notice that there would be two vectors that are perpendicular to that plane, one going up and one going down. Deciding which is the correct one is determined by the right-hand rule. The right-hand rule applies to all cross products, and it says that the cross product is your thumb, and the other two things are your vectors in order. Your index finger is the first one, A, and your middle finger is the second one, B. And honestly, I kind of use all three of my fingers for B, just because that's how I was taught. But really it doesn't matter as long as you know your directions correctly. So if we're going to apply this to QV cross B, which is the formula for the force, you would say the first thing is V, the first part of the cross product. So it's your index finger. And then the second part of the cross product is B, which conveniently is B down here, your middle finger or all the rest of your fingers. And the cross product, the force, is going up. And it's Q times the magnitudes of those things, but the direction still applies. So you would say this is the velocity, this is the field, and this is the force. Now, one thing you can do is you can change this angle between your fingers to match the alpha if you want to. It's not super important, but you can. Another consequence I would like to note real quickly is that if your A and your B, your velocity and your field are pointed in the same direction, that force actually turns out to be zero, because if you do force equals Q, V, B, pretend those are all magnitudes, sine alpha, and your alpha is 0, sine of 0 is 0. So your force would equal 0 when alpha equals 0. So if your velocity and your field are going the same direction, like your A and your B, your fingers would be closed, there is no force. However, because things have to be difficult, this only applies to positive particles. So you'd say force equals QVB sine alpha. Using that for directions only works when Q is positive. If Q is negative, it goes the opposite direction of what you would expect. Or you could just include that negative there, say it's negative QVB sine alpha equals force, and then the force would end up being negative, which would mean it's going the opposite direction of what you expect. You can also, if you feel like it, use your left hand for negative particles. So you do the left hand rule and get everything backwards. Any of those methods works. You just have to know negative particles, like electrons, go opposite the direction that you would find with the right hand rule. Here's an example for you. We've got a proton right here in this magnetic field. At that point in the picture, the magnetic field, which I'll represent by, let's say, a blue arrow, is headed to the left. Now, you couldn't use that as like a line. I'm just showing the vector tangential to its path or its line in the field. So that's going to be our B. So we say force equals QV cross B. So you take the V as your pointer finger, your index finger, point your index finger in the direction of V, then take the rest of your fingers, point them in the direction of B, and look and see where your thumb is pointing. Your thumb should be pointing up out of the page, which is represented by a dot. So we'd say force represented by a dot. It is out of the screen because this is a proton. And yeah, that would be all it is. It's out of the screen. For an electron, you could say, well, the right-hand rule predicts out of the screen, so an electron has to be backwards from that, so it'd be into the screen. Or you could say force equals negative QV times B, which would mean force equals negative what you had predicted, so opposite what you had predicted. Or you could do your left hand. You could say V is my pointer finger, and B is the rest of my fingers. And if you use your left hand, you get your thumb pointing down into the screen, which would be the direction for the for the electron. Here's another example. This time we are in a uniform magnetic field. Your smartphone has a built-in digital compass without an actual needle, and it uses the force on electrons in a conductor to figure this out. That's how the sensor works. So this picture shows one of the electrons moving to the right, and the Earth's field points up on the page. So let's look at the direction of the magnetic force. You'd say V is your pointer finger, and B is the rest of your fingers. Now this is an electron, so you can either do the right-hand rule and flip whatever your result you get, or you can do the left-hand rule. I do the left-hand rule personally, but it's your preference. So we'll say V is the pointer finger, B is the electric field, which is pointed up to the top of the page. If I do that, my left hand's thumb is pointed into the page. So that is the direction of the magnetic force. Now, something that is a very, very peculiar result about magnetic fields is that due to the nature of the cross product, the force is always perpendicular to the velocity. Always. That's how a cross product works. That's how magnetic force works. And if force is perpendicular to velocity, and force is mass times acceleration, that means acceleration is perpendicular to velocity. And perpendicular acceleration to velocity is really only a thing of rotational motion, which I know is like a taboo, scary, gross subject that no high school teacher ever wants to touch. So yeah, I know you're probably not super familiar with rotational motion. But if you've got a force that is acting perpendicular to a velocity, like here, and your acceleration is perpendicular to your velocity, you're not speeding up at all. The acceleration doesn't speed the particle up. It instead moves it in a circle, on a circular path. So if you have a charged particle that is moving in a uniform magnetic field, it's going to be doing a circle with a certain radius. And I'm not going to go through all of the rotational derivations, but that path is given, or that force and path are given right here. The force equals mv squared over r. This is not specific to magnetism. This is just a general result of like rotational kinematics, rotational mechanics, that force equals mv squared over r. That's just the thing that comes from mechanics. And the force in a magnetic field is QV cross B equals mv squared over r. So you can figure out from the field and the charge of the particle and its initial velocity, the circle's radius that it will be moving in based on its mass, all those fun things. So its trajectory, the thing you really need to know is that the trajectory of a charged particle in a magnetic field is going to be moving in a circle with a specific radius r that's based on all of those parameters. All right, so last peculiar thing before I let you go work on some homework is that the magnetic force acts perpendicular to both magnetic field and particle velocity. That's the thing from the cross products in the right-hand rule, which means that magnetic fields can't change the speed of the particle, only the direction. And that's because we said velocity is always going to be perpendicular to force. So the acceleration is always perpendicular to the velocity, which means we're only going to be changing direction and never speed, because acceleration has to be in the same direction as velocity in order to change the speed. So we're never changing speed, only direction. Which begs the question, or some people might concede that it begs the question, if magnetic fields can do work, because kinetic energy, or work, is a change in energy, and if you're changing kinetic energy, you have to be adding speed, and if you're in a uniform magnetic field, then you're not gaining potential energy any which way. So the answer is no, magnetic fields cannot do work on a particle that's only moving with translational velocity. But we do know that magnets can attract other magnets, pulling them, moving them, which does work. And so the deal with that is that is based on that angular momentum, the angular spin, the magnetic moment, that is a property of particles that have charge and spin. So that only works on things that have that angular motion. If you're looking at only translational motion, then no, magnetic fields can't do work. If you're looking at angular, then yes, they can do work. But for translational, it's no. So you might hear somewhere or even read somewhere that magnetic fields cannot do work, which is true for translational classical particles. But in reality, with quantum mechanics, with the spin of particles, it is possible for magnets to do work. All right, you guys have a good day. Go work on some homework. Let me know if you have any questions. Have a good day.